We will now look at another energy storage device called the inductor. The capacitor and inductor are both energy storage devices. Unlike resistors, which dissipate energy, inductors and capacitors store energy. They do not dissipate energy. So if you pump energy into these devices, rather than dissipating it, they store the energy. Okay, so you can then recover the energy from either capacitors or inductors and use it elsewhere. Both of these are very, very interesting devices. And one of the real interesting features comes from the fact that these two are duals of each other. Okay, duals means that if you understand how to build circuits and understand the properties of one of them, by making a few simple transformations, you can actually divine the relationships for the other element. Okay, so for example, if you build a circuit containing one element with voltage sources, you can build similar kinds of circuits with the other element containing current sources. Okay, we'll see some examples of this, and the two are very, very complementary to each other. Let's dive into details of the inductor and build the relationship between the capacitor and inductor as well. Okay, we will study the ideal linear inductor in 6002X. You've most likely seen inductors in your high school physics, advanced physics courses. So here is one example of an inductor. So a physical structure for an inductor might look like this. I have some core with a magnetic permeability given by mu. And let me go ahead and wrap a coil of wire around it, like so. Okay, with some turns of the wire. And I wrap those turns of the wire around this coil. This is an inductor. In general, I can associate inductance with any loop of wire. So in this case, let's say, for example, I have some current I flowing through this wire here, which has been looped around the core. And I have some voltage V between the two terminals of the wire that has been looped around. Let us say I have N turns of wire, and let us also say that the area of this core is A. Okay, and then let's assume that the circumference of this core is L. Okay, so my basic construct is that I have a core with magnetic permeability mu. It has cross-sectional area A, N turns of wire coiled around it, and I have a voltage V across it and a current I going into it. Let us also say that it has a total amount of magnetic flux linked to it, lambda. Okay, so lambda is total flux linked with the wire coil. Okay, so total flux linked. Okay, so when I pass a current through this coil of wire, I get a magnetic flux that links with each of these turns of the wire, and add them all up, I get a total flux linked called that I'm going to call lambda. Okay, so we get a relationship that looks like this. This particular construct here has an inductance L given by the following physical properties. Mu, the permeability, N squared A divided by L. Okay, so the inductance of this is given by mu N squared A divided by L. Okay, I can represent this inductance, this little inductor, as a symbol, electrical symbol like this. Okay, I give it a symbol, a little coil of wire with inductance L, and I can apply my usual terminal pair of voltage and current across it and through it. Okay, so this is my electrical symbol lambda. Electrical symbol for the inductor with inductance L. Much like a capacitor, which had its capacitance given by the formula, let me write that down here as reference. I'll do the capacitor stuff in green, so as not to confuse you. So for the capacitor, we had gotten C was equal to epsilon A by D. Okay, so L, the inductance, is mu N squared A divided by L, which are the properties of this little structure to the left of it. And this is similar to what I did for a capacitor, where the capacitance of two parallel plates was given by epsilon A by D. Okay, so this was for a capacitor. So let me just put that in a box just to show that it is just for your reference to show you how both inductor and capacitor are related. Okay. Now, much like for the capacitor, where we had a relationship between charge and capacitance and voltage, for the inductor, we have a relationship between the magnetic flux, lambda, and the inductance and the current through it. So this relationship is given by lambda equals Li. So I is in amps. Okay, that is the current that is flowing through it. L is the inductance in henries. Okay, it's inductance in henries, and the total magnetic flux linked by the coil is given by lambda, and the unit for that is it's in Webers. Okay, so lambda equals Li, and that relates the magnetic flux that is linked with the coil as being equal to Li, where L is the inductance and I is the current flowing through the coil. Now, recall the similar expression, or at least the expression that was similar in spirit to the inductance that we studied earlier, and let me write that down for you in green as well. So for a capacitor, the corresponding term was Q equals CV, where Q was the charge in the capacitor, C was the capacitance, and V was the voltage. Okay, so right here you will notice a bunch of interesting things. Okay, first of all, you will notice that where I had Q on the capacitor, for the magnetic flux, for the inductor, I have the magnetic flux. Where I had the capacitance, I have the inductance. And where I had the voltage previously, I have a current. You can read more details about the inductor and the basic properties of materials, the permeability and things like that in section 9.1.2 of the textbook.